This video is about how complex zeros come in conjugate pairs. For our notes, we need to recall some important things. First of all, when we say a plus bi, remember that's a standard complex number form. Okay, but then a minus bi, if you pair that with it, those are called complex conjugates. And then secondly, our complete factorization theorem states that if p of x is a polynomial of degree n is greater than or equal to 1, then there exists complex numbers a, c1, c2, and so on, with a not equal to 0, such that we could write p of x, our polynomial, in completely factored form, right? A is the leading coefficient, and then all the factors are binomials, such as x minus c1, x minus c2, and so on. Now we're also going to add to that the conjugate zeros theorem, which states as follows: if the polynomial p has real coefficients, and if the complex number z is a zero of p, then its complex conjugate is also a zero of p. Simply put, as we'll see in examples, let's just suppose that 2 plus I is a zero of some polynomial. Well, then what we can automatically assume is that its complex conjugate would also be a zero. That means we would also know in this case that 2 minus I must be a zero as well. Let's try an example where we want to find a polynomial with integer coefficients that satisfies the following conditions. So p, the name of our polynomial, has degree 3, and it has zeros -3 and 1 plus I. Now let's immediately recognize that given our theorem, if 1 plus I is a root, that automatically means, of course that's a complex root, that means its complex conjugate is also a root. So though it's not listed, it is implied that 1 minus I should also be a root. Now we can define our polynomial as p of x, and we can write it in factored form given our theorem above, where a is the leading coefficient, and then all the factors of this polynomials could just be written as x minus c, or c1, c2, where c's are all the roots, or the zeros. In other words, I could say x minus -3, since that's one of my zeros given, and I can say that that is one of my factors of this polynomial. We want to keep this going with all remaining zeros. We have the complex conjugate pair that's left. So in the same way, I'm going to write x minus each of these roots. Now, since there are two terms, I'm going to put them in parentheses so that x minus 1 plus I is my next factor in this polynomial. And then my third and last factor is going to be x minus 1 minus I, where again 1 minus I was that extra complex conjugate root that we found from our given information. Now we need to turn this into a much better looking polynomial. In fact, we'd like to eventually eliminate all the i's from it so that there's nothing imaginary. And then we'll have to figure out what we're going to do with this a, the leading coefficient, but that won't be too difficult. I think we'll wait till the end on that. For now, let's go ahead and just simplify by recopying and distributing negatives as needed. So we'll rewrite this as a, and then this is really an x plus 3 if I put these negatives together, times, and then this next factor has a negative that could be distributed, which would make this x minus 1 minus I. And then thirdly, I can do the same with the negative and get as our last factor x minus 1 plus I. Now, if you go back to our problem and recognize that we want to find a polynomial with integer coefficients, that means let's keep going here to expand. We don't want imaginary units floating around, and so let's expand what we have, which is just going to be a kind of hold your nose and do the algebra step. There's nothing really pretty about it. We're going to say p of x equals, I'm going to keep this a out front for now, and the real problem we have right now is these imaginary units inside these second two factors, or the last two factors. So I'm going to keep the x plus 3 as it is even, but then think about how to multiply these two trinomials together. So just be careful and stay organized. We're going to multiply every term in the first factor by every term in the second one, starting with the x. So x times x would give us x squared, x times negative 1 would be negative x times I would be plus ix. Now we'll start over with this negative 1 getting distributed all the way through, so we'll say minus x plus 1, and then minus I. And now the negative I going all the way through, that would be minus ix plus I, and then minus I squared. Like I said, it's really not pretty, but if you stay organized and just go carefully through the algebra, it's not too bad. Now, what should happen at this step is that things should start to cancel out. If we look very carefully here, notice there's a positive ix or plus ix and a minus ix term. Those would cancel right out. Also notice there's a minus I and a plus I. Those would cancel out. Notice that other terms are just real number coefficient terms that could be combined and simplified. But then also at the very end we have this minus I squared term. Well, I squared is really negative 1, so this is really a negative 1 term that we have going on at the end. So we'll use that when we combine these. So let's just try to recopy and clean up what we have. We have p of x equals a. We're ignoring that a for now still. And then we had an x plus 3 after it. And then if we combine like terms inside this mess at the end, we have an x squared term. Then we have, let's see, minus x and minus x would be minus 2x. And then to look for our constant terms, we have a plus 1. And then don't forget about at the very end, we had this minus 1. That's also really a plus 1. So put those together and we should get plus 2. And let's go ahead and keep going here. We want to, at this point, expand by multiplying the binomial x plus 3 times this trinomial. So we can separate this into a bunch of individual terms. We're going to keep the a out front, and then just be really careful with this step as well. We're distributing the x to all 3 terms in the trinomial that follows, which will give us x cubed minus 2x squared plus 2x. Now we're going to distribute the 3 all the way through to say plus 3x squared minus 6x and then plus 6. Now at this point we can look to combine any like terms, and let's do that to rewrite again and get a times x cubed, and then notice there's an x squared term here and here. We'll put those together for a positive x squared. Then we'll put our x terms together, plus 2x and minus 6x would be minus 4x, and then we have the plus 6 on the end. Okay, now if we go back to the original problem, we'll read that all we wanted to do was find a polynomial with integer coefficients that satisfies the following conditions. Well, all the conditions, which were that it has degree 3 and zeros as given, so far are lining up, right? Notice this polynomial would have degree 3 because the leading term has a power of 3. And so far, the coefficients for all of these x terms are all integers. Now, it could be the case that if somehow one of those coefficients was a fraction, then we would pick a number for a. Yes, we're going to pick any number for a that would clear that fraction for all these terms when distributed through. But since we don't have any fractions in this case, all of our coefficients are already integers, we're just going to pick anything we want for a, and let's make our lives as easy as possible. Let's just let a equal 1, because then we could say p of x, our polynomial, is simply x cubed plus x squared minus 4x plus 6, and that satisfies our original conditions we wanted. It's degree 3, as we stated earlier. It has the zeros they gave us because we baked those right into this whole process to get this polynomial, and it has integer coefficients, which would be all the numbers in front of all of our terms here. Now, if you happen to be doing a problem that's somewhat similar to this, but not exactly written in this way, one other thing that sometimes is present in a problem like this is that in all these conditions, they might say at the end, like, by the way, they might give you a number like f of 1 equals 6 or something like that. If they do, in some kind of textbook, that's because they want you to use that to find out exactly what a should be, in which case you would just plug in the x input they give you for x and then set the whole thing equal to the value they give you, and then that way you'd still have your a and then use the equation you just got by plugging in those numbers from the condition to find out exactly what a should be. So it's a very similar kind of problem, just a maybe slightly different step at the end. This one happened to be worded in a way that just said get integer coefficients.